This is the illustrative video for ECCV 2022 paper, Disentangling Object Motion and Occlusion for Unsupervised Multi-Frame Monocular Depth. Retrieving 3D information is crucial for autonomous vehicles, robots, and AR/VR applications. Unsupervised monocular depth prediction provides an efficient solution. The self-supervision and the multi-frame cost volume are based on the reprojection geometry. They employ an additional pose net to predict camera ego motion from adjacent frames. The predicted depth map and pose are used for reprojection. Image from time t is projected to the 3D space and then reprojected back to t-1 image plane. Conventional methods suppose the reprojected image will match the t-1 image. The training loss and the cost volume are based on the reprojection consistency, which is based on the static environment assumption, does not hold for most real-world scenarios. Suppose the dynamic object moves from Wt-1 to Wt. The reprojected image will mismatch even if the depth and pose prediction are perfect, which will mislead the model training. Another problem is backgrounds visible at current time will be occluded at the previous time, which will introduce noise to the model training and inference. To solve these mismatch and occlusion problems, we accordingly propose a novel multi-frame monocular depth prediction method called dynamic depth. We first predict an initial depth prior, which is sent to the dynamic object motion disentanglement module to solve the mismatch problem. The occlusion-aware cost volume is constructed for the final depth prediction. Our framework is trained by a novel cycle-consistent training scheme. To summarize, our contributions are as follows. First, we propose a novel dynamic object motion disentanglement module that leverages a depth prior prediction to solve the mismatch problem in the final depth prediction. Second, we devise a dynamic object cycle consistent training scheme to mutually reinforce the prior depth and the final depth prediction. Third, we design an occlusion-aware cost volume and reprojection loss to alleviate the occlusion problem. With these innovations, our method significantly outperforms existing state-of-the-art methods on the cityscapes and KT datasets. In the DOMD module, we first simply predict a prior depth to project the dynamic object image patch to 3D space and project back to the t-1 image plane. Our DOMD module will replace the original image patch at time t-1 with the projected patch to form the disentangled image. In the aforementioned geometry, when we replace the original image t-1 with the disentangled image, the loss and cost will correctly match at Wt. Our DOMD successfully disentangled the object motion and provides prior knowledge to the final depth prediction. The pixels of backgrounds in the black area is occluded by the dynamic object at time t1. To alleviate this problem, we propose an occlusion-aware cost volume for geometric reasoning across temporal frames. Feature map of the disentangled image is warped with multiple pre-defined depth hypotheses to the current image plane. The L1 differences with the current feature is used to construct the cost volume. Based on an observation that the black occlusion area in the cost volume is usually different between layers, we propose to replace these occlusions with nearby non-occluded areas' cost values. This preserves the global cost distribution and leads the training gradients to flow to non-occluded areas. We further propose an occlusion-aware reprojection loss. The backgrounds occluded at time t-1 are usually visible at t+1 and vice versa. These occlusion areas will generate noisy reprojection errors. Using the non-occluded source frame error for each pixel can avoid most of the occlusions. The widely used per pixel minimum loss function does not work for all pixels, while our occlusion-aware loss always correctly chooses the non-occluded area. Finally, our cycle consistency loss enables the final depth prediction to backward guide the learning of the depth prior prediction to achieve a mutual reinforcement learning scheme. Note that our prior depth prediction model does not need to be accurate at the beginning of the training. It is trained from scratch and simultaneously improve itself with the final depth prediction during the training. Suppose the depth prior prediction is inaccurate. The reprojected image patch will occlude some background pixels which are visible at time t. those pixels will generate a higher photometric error in the reprojection loss. To minimize them, our network will manage to decode the error of depth prior prediction from the disentangled image IDT-1 to predict a better final depth and improve the depth prior prediction by our cycle consistency loss. We perform an extensive quantitative evaluation on the cityscapes and KT dataset. Our method significantly outperforms existing state-of-the-art methods on both datasets. We show an even larger advantage on the dynamic object areas. We further show qualitative evaluations on the cityscape testing set. Conventional monocular depth prediction methods like mini-depth make severe mistakes on dynamic object areas due to mismatch and occlusion problems introduced by object motions. Our method achieved significant improvement with our proposed dynamic object motion disentanglement and occlusion alleviation.